Thank you. Illustrious introduction there. So my name's Phil, and today I'm going to be talking about the meaning of artificial life. And it's a talk where we're going to talk about the history of AI. We're going to talk about its origins, and I'm going to bring that through to today. And then we're going to see how AI is evolving in today's industry. And along the way, we'll also learn a little bit about the word that I prefer as data science. So if we think about for a moment that we're going to think about what people think AI is, and they'll probably go back to some sci-fi. I think that's where the origins of AI really came from. And in particular, there's probably two books/film that really kicked it off. The first, the I, Robot by Isaac Asimov, a very, very famous book now, where the 3 laws of robotics originally came from. And it's interesting to note that that actual story was written in 1942, so it's very, very, very old. And the book, I, Robot, the collection of short stories, was published in about 1950. That was, one of the first real defining moments in literature where AI was first considered. Then we've got 2001: Space Odyssey, a story about a psychotic artificial intelligence which attempted to kill the crew on board a space station in order to save its own soul. And that was in 1968, so quite a few years after. And that was actually produced at the height of when people started to think about the bad side of AI. But in fact, the whole thing actually goes a lot further back than 1940, 1968. Even in mythology, there's lots of references to various automated agents. In Greek mythology, Talos was a bronze automaton, and he was created by the god Hephaestus. He was given to Europa by Zeus to protect her when she was on the island of Crete. He would go around throwing rocks at pirates that anybody just tried to invade the island. So I like the idea that gods also need holidays on Crete as well. And even in other cultures as well, in China, there's lots of stories about people creating human robots. I think the word was, engineers that would create mechanical men to impress the emperor at the time. So throughout any number of cultures, there's lots of references to automated agents. Into the Dark Ages, I think the stories get a little bit more dubious. In 1206, it's quite an old reference, a chap called Al-Jazari created a programmable orchestra of mechanical human beings. But my favorite, in around 1500, a guy called Paracelsus claimed to have created an artificial life out of magnetism, alchemy, and sperm. Now, I would not like to have been there during his experiments, and I suspect that was probably the birth of the sex toy industry right there and then in 1500. So slightly questionable. A few others, and there's even serious thinkers. René Descartes, he proposed that animals ultimately were just complex forms of machines. So we're starting to see throughout the history into the Dark Ages that these ideas are a little bit dubious, but people were certainly thinking about it a long, long time ago. During the Renaissance and after the Renaissance, things started to get a little bit more serious. Thomas Hobbes published Leviathan in their Reason is Nothing But Reckoning. And actually, I just in the British Library in London, they've got a display on at the moment which has a first edition of Leviathan. And to think that it was written such a long time ago, it's hugely impressive. So I'd recommend that you go and see that. It's totally free. In 1642, Blaise Pascal, he among many other things, he invented the first calculator. And this is really the first, real-life examples of machines that can mimic some parts of human thought. So he got a lot of acclaim at that time. Gottfried Leibniz was very prolific. He was the guy that who independently found differential calculus. He invented the binary counting system, and But more interestingly, he had some other things that were maybe a bit more audacious, but people forget. He attempted to work on assigning a specific number to all thoughts that human beings could ever have in order to try and create an algebraic solution to thinking. Obviously, that didn't work too well, but at least he tried. But really, it was just before the 1950s and around the 1950s where things started to come together as a field. And it was not really due to one person. One person was very influential, but it was actually a confluence of many different things. So one of the first ones is that it was found that the brain was actually it was constructed from a very large amount of electrical components, and the brain was thought at the time to represent and replicate an electrical circuit. And that was a key discovery. Claude Shannon also around that time defined his definition of what information is and how we can quantify it. Probably one of the most important people of all was Alan Turing, and he in this particular instance he came up with a theory of computation, which basically defined the functional limitations of a computing engine. And that was really important because it showed that the only real limitations was the processing power of the machine itself. And these ideas and more started to raise the idea that the belief that we could actually create an artificial brain. So much so that in around 1950 we started seeing the first implementations of an artificial brain. So think of this as Professor DeAndreas's drones, but much earlier. A guy called William Gray Walter, he started playing with robots, and I say they were very simple, but I mean they were quite complex at the time, but now they seem quite simple. All they're comprised of were a phototube, which is like a light bulb that's filled with a gas, where the resistance changes depending on whether photons hit the gas or not. And they were connected to vacuum amplifiers and then fed into motors. So the idea was that this thing could follow light. You showed it to light and it would go towards the light. And that in itself was really cool, but he played a little trick on people to make it seem like they were far more intelligent than they were. And it was this. What he did, he placed lights on wall sockets, on plugs on the wall. And whenever the robot's battery started to drain, it would drive towards that light and plug itself back in and charge it back up. So it was just a simple modification of his robot that gave the impression that it was really intelligent. It was feeding itself. It was looking after itself. And that's generally thought of as one of the first intelligent robots. But really the seminal moment was the definition of the Turing test in the paper Computing Machinery and Intelligence. And in this, Alan Turing started to think about what thinking actually is. And he came to the conclusion there wasn't really a clear definition of what thinking was, so he created his own. And his idea of what thinking is if you can fool a human into thinking that a computer is actually a human, then you can define it as thinking. And this changed the game completely because it constrained the problem. It made the problem a lot more simpler than it was previously. For the first time, making machines think seemed like a problem that people could solve. And just to think about the ideas at that time, this is a quote from John von Neumann, a famous mathematician. He was in a lecture and he was asked the question, I don't think that computers and machines will ever be able to think. How can they possibly think? I do such complex things, we can't possibly get a computer to do that. And he said that you insist there's something a machine cannot do. If you will tell me precisely what a machine cannot do, then I can always make a machine that will do just that. And this was actually a key insight, and I think this is that was 1948 he said that. And the problem was, people still didn't really grasp that idea. It took around 30 or 40 years, as we'll see a bit later on, for people to realize that that's what we've got to do. We've not got to try and make this generalized idea of a human brain. People ran with the idea. The Church-Turing thesis a few years later came out and said that, in essence, any algorithm that a human can use to do something, we can encode in machine form. So, for example, if we can define an algorithm for sorting letters in a post office and putting them in a certain box, if we can define an algorithm for that, we can encode that in software, in a machine, relatively easily. So it's just a general theory to say that the algorithms can be encoded in machine form. But then there was an extension to this by David Deutsch, and he attempted to prove that there's an extension to this, that any physical process that could be simulated by a universal computing machine could be performed by a machine. And there's a couple of caveats to that, and basically the caveats again came down to computational power. We need to be able to simulate and predict that happening in real time, otherwise it doesn't make sense. But that got everybody excited, because in theory, if we have a computer that is powerful enough, we can simulate any natural process at all, and that includes us. So between 1955 and 1970, there was a real boom in AI. There were vast sums of money that was poured into to doing AI research. And one of those examples is that DARPA, the military funding agency, funded MIT's AI lab to the tune of $25 million a year. And that was totally unstructured, open funding. That was money that they could spend in any way. And also around that time, some very, very intelligent people started making predictions about what would happen when. They saw this progress. This confluence happened only over about 5 or 10 years when people started thinking about trying to make a human brain. So they were simply extrapolating over the next 5 or 10 years, and they suggested things like they would beat the world chess champion, in 10 years, a new mathematical theorem. Machines would be capable within 20 years of doing any work a man can do. So that was quite audacious. And, as you probably know, that all popped, that all bust. And the reason was people just became disenfranchised with the idea of AI because they saw nothing. They saw all of this grandiose ideas and predictions of around 1955 and 1960, but nothing came of it. And in the, oops, I've got a typo there. In the UK, at least, in 1973, the Lighthill report, it was a government-sponsored report, criticised the utter failure of AI to achieve its grandiose objectives. And it completely led to the dismantling of AI research in the UK entirely. And it's a real shame, because up until that point, actually, the UK was quite at the forefront of AI research, and now it's not. It's all in the US because we lost all the funding. But to be honest, you can criticize them a little bit because they should have realized this. These are smart people. But it wasn't really their fault. The real limitations were a limited amount of computational power. So just as an example, processors at the time, 65, 70, they could manage around 1 million instructions per second. Current machine vision implementations need somewhere between 10,000 and 1 million instructions per second. So this was orders of magnitude away from where they needed to be. There's also a technical limitation that they found as well. It's called the curse of dimensionality. So a dimension is a technical term. My height, my age, my eye color, they're all dimensions in a data set. So that would be 3 dimensions. And many of these vision-like problems, for example, are very highly multidimensional. And a lot of the problems can only be solved in exponential time. So that means every time we add a new dimension, it takes an exponentially amount of time longer to solve that. And finally, one of the most interesting, I think, and the coolest one, is how to encode common sense knowledge. Many problems, like if you just imagine how you see things, you have a set of rules and encodings and laws that you've learned over your lifetime, and you expect those to be true. You assume those to be true. So if you saw a picture where somebody was hovering upside down, you would instantly recognize there was something wrong with that picture. But trying to teach a machine how to do that is incredibly difficult, because it means we need to provide examples of people hovering upside down. And I think one of the best ways of demonstrating that is with my children. I love talking about my children because I like looking at how they learn, and it correlates so well with how machines learn. So this is a painting that she drew when she was about 3. She was about 3 when she drew this. And can anyone in the audience suggest what that might be? Jellyfish, face. Oh, did someone say elephant then? Yeah. Wow, you've got an abstract brain. I don't see an elephant there. You must be a fan of Picasso or something. So yeah, jellyfish, great hat. Person, and that's exactly what we thought, but she actually told us something different, and we didn't understand what she meant until we turned it upside down. And it's actually a cup of tea. See the cup, the handle, the steam from the tea? It's a fantastic drawing of a cup of tea. She drew that upside down. So it made no sense to us. She, in her 3-year-old mind, hasn't quite learned that steam has to go up. For her, steam can easily go down as well. So, if we can't even recognize that, how on earth can we teach a machine that steam has to go? We have to teach it thermodynamics just to do a visual problem. It's insane. And finally, we get to the 1980s. And this is really when we go back to von Neumann's comment, and people realize that the only practical problems that could be solved are, expert problems where we really constrain the problem. And this was called the rise of the expert system. And just as an example of that, if somebody came to me, a client came to me and said, I want a system that's capable of handling orders by speech. That's a hugely unconstrained problem, and that would be very hard to solve because you'd need an algorithm that was able to take any text and just convert any speech, and convert that into text. Some sort of knowledge about ordering and systems and things like that. Incredibly problem. But if we convert it, if we try and constrain the problem a little bit, it becomes a lot easier. If we suggest that the product will place orders given by speech for some combination of meat and potatoes, which is apparently all you eat in Berlin. So it's got to be a combination of meat and potatoes. And in Berlin, we're constraining the problem because it becomes a lot easier now. The only thing that people can order is meat or potatoes. You've only got 2 things there. If you're in Berlin, we get some examples of somebody speaking German, or probably English, actually. Everyone speaks English, which is incredible. But because we've constrained the problem, it becomes a lot easier. We could do something like a simple distance measure to say, like, how similar was the sound from that person to the new observation that we've just seen. And in around the 2000s, some of these predictions that had finally started to come true. And it had been 50 years since Turing had done all of his amazing work. But in about 1997, one of the predictions, the one by H.A. Simon, beating the world chess champion actually came true. And it was done by this big black box called Deep Blue. And of course, it has to be a big black box because it's built by IBM. They sell big black boxes. I'm sure inside there was either just a little laptop or a single PU. Maybe a person, actually. That is big enough to be... I bet now that when he actually won that chess competition, the guy, that was his tomb. He wasn't allowed to get out of it because he actually beat the world chess champion and he had to be entombed for future posterity. And that was 39 years after the initial prediction by H.A. Simon. And it took all that time, basically, to realize that we can't solve these grandiose problems. We need to constrain ourselves. One of my favorite examples is in 2004 and 2005, DARPA funded the Grand Challenge. And remember, DARPA is the same agency that funded the initial AI research in MIT's AI lab about 40 years ago. And 50 years ago. And they started to pour money back into AI again. And this was a task for a robot to drive autonomously through 131 miles along an unrehearsed desert track. So this was an incredibly difficult problem to solve at the time. One of my mentors, Greg Duckworth, was actually working for DARPA at the time, and he had the task of sitting in this chase car. You see this car in the background here, because the cars in front were completely autonomous. There was nobody inside it. They had to do that to ensure that there was no cheating, basically. So they had a chase car which followed the car to ensure safety and things like that. And inside that car, they had some buttons they could press. They had 2 buttons. They had one, a little red button, which was like a pause, which would pause the software working inside the car and allow it to come to a graceful stop. The second one was a kill switch, and knowing the Americans, it would probably blow something up somewhere. I don't know if it would blow up the car or the mountain or what, but something would probably blow up. And they were following, sorry, any Americans in the audience, and they were following this car, and all of a sudden, at about 20 miles in, the car suddenly veered off course and started raging through the desert. And they tried pressing the software pause, and it didn't work. It didn't respond. It kept going. And you see, this is a good picture because it demonstrates the type of terrain that they were in. You know, there's huge boulders, you know, bushes and trees, and it was plowing through all of this and totally trashing the car. And these guys actually struggled to keep up because they couldn't get through that terrain. And eventually, after following it for a little bit, they were ready to press the kill switch and blow it up. But they didn't really want to do that because they wanted to give it an opportunity to stop. And finally, it did stop, but all of its own accord. They didn't do anything. It just stopped mysteriously. So when they got out, you know, they tentatively tiptoed up to this car and, like, you know, with the back of the hand, just sort of touched it like that, just in case it would bite them or something. You know, they checked the exhaust and the engine wasn't running, and so they thought, okay, it must be safe. And they popped the bonnet, and it turned out that the battery lead had come off as it was going over all of that rough terrain. And that had caused a full system reset, and the car had just stopped because everything had stopped working. So that was why it stopped, but it didn't explain why it went berserk in the first place. And so they went back to the hotel, and they started looking through all the logs, and they found a mysterious log entry, which it just suddenly stopped. It stopped at 22 degrees right, 0.5 acceleration, and that was the last log entry. And it turned out that because they were using C++, somebody had accidentally made a memory leak, and after exactly 21 miles of operation, it filled up all the RAM in the computer. And so it was unresponsive to any OS commands, anything, and that's why the software pause didn't work. It was just a memory leak, you know? Nightmare. So these complex systems, these dynamic systems, these systems that are supposed to have feedback can still come a crop up just because of a memory leak. So why is this all happening now? And it's interesting to note that it's not due to any one particularly smart people, even though there's lots of very smart people working on this problem. It's not due to a new paradigm. You know, it's not due to a new fad or craze or technology. It's purely down to computational power. Back in 1951, there was a computer made by a company called Ferranti, which is an old company in Manchester in the UK. And they went bust about 30 years ago, unfortunately, but they built a computer called Mark I, and that had a performance of 800 instructions per second. And at that time, a chap at the University of Manchester encoded a chess-winning algorithm on that machine. But the problem was, it took 2 hours to make one single move. So an entire game would take like 50 years. So it was just unfeasible to actually use it to actually beat anybody. But all of the stuff existed at that time. And it took until, 46 years later until we had something that was generally good enough to be able to compute that in real time. And even today, in 2016, an iCore 7 has 317 billion instructions per second. You know, these are many, many, many orders of magnitude greater than we've had previously. And that's it. That's the only reason why we can do all of this amazing stuff now. So, do we see AI now? Are we going to see AI as a thing? Yes and no, unfortunately. Yes, in a sense, if we take Hobbes and Turing's definition of what intelligence is, then yes, definitely, we can do that right now. You know, we can drive cars using machines better than a human could. Actually, and I had an interesting chat with a guy in one of my training courses the day before yesterday, and he works for a company that helps regulators define tests for advanced systems such as automated cars. And they said they're having real problems trying to define regulations for automated cars because the systems are so complex. Normally, basically now the regulators are still doing like Apollo-style verification of systems. You know, you go through the code line by line and you verify that it does exactly what it's supposed to do. But in these systems, they're so complex, we can't do that anymore. So there needs to be a shift, a change in the way that regulators do testing. You know, we've embraced unit tests for decades now as software engineers, but that's still not happening in the regulators. So we need to change that. We need to force the regulators to change that because that's the only way we're going to move forward. So yeah, cars, talking about like computer vision problems, we can do many things much better than a human can now. So in terms of that definition, yes, we've got it. But for engineers, I think the argument is interesting, but we're kind of missing the point. And this brings me to my main point. Stop saying AI. It doesn't make sense. It's a philosophical debate about what intelligent is. It has no bearing on engineering. I think it's more about a question of what is the definition of a machine. Like if you say that, okay, humans can think, but we've kind of already proven that we're just, again, complex biological networks. Can that be classed as a machine? Are we just machines? If we're machines, then they're definitely sentient as well, because that's just a machine as well. It's a philosophical debate. So I know as engineers, you're probably aware of this, and that's fair enough. But when you go back, go to your marketing department and say, stop saying AI. Please stop saying it, because it will blow up in everybody's face. Because at the moment, it's being used just like every other craze before it, all the big datas and everything before that. Eventually, it will peter out because people will stop believing you. They've heard it all before, and because of that, the whole field will suffer. So stop saying it. And I prefer, instead, to use a term called data science. And I prefer data science because it demonstrates the multidisciplinary approach that's required to work with data these days. The definition by I can't remember her name now, a lady who wrote the book Doing Data Science. I like hers the best, and it says that a data scientist is someone that's better at software engineering than a statistician, a software engineer that's better at statistics than other software engineers. And I add my own as well and say that I think it's important for employees to be consultants as well. People are generally more consultants than they are employees. So that kind of in a nutshell is what data science is. But it does comprise of several disciplines which have emerged over time from different fields. And this is an attempt to try and put some of those things into context. I actually worry, when I drew this picture, I thought it was great. It looked a bit like a Venn diagram, but now I apologize because it looks a little phallic. I heard a story the other day. Apparently on Westminster Bridge, there's like these really ornate railings, which are like a fleur-de-lis on them. And when the sun, goes low, these fleur-de-lis suddenly extend into these very rude shapes across the bridge. And I'm sure that wasn't an intention, and that wasn't my intention either, so I apologize. But the idea is that all of these places, all of these fields and techniques have all come from different places. Some have come from the business side, some have come from just the fact that we're using a huge amount of data, and some have come from the idea of trying to implement automation. So let's take a little bit of time just going through those fields if you haven't seen them before. So the first one, and probably the most famous, is machine learning. And this is the practice of automating some data-driven process. So I like to say that software and software engineering is the automation of a process, of a business process. There's very hard fact, there's very closed rules that you can apply to encode this into software. Something like a chess-winning algorithm. It's just a series of rules that we have to follow to get to an end. Machine learning is doing a similar thing, but it's doing it with decisions instead. We're trying to replicate the decision-making process, the judgment that somebody makes when they're trying to, whether they're trying to establish whether someone's worthy of having a loan or not. That is a judgment call. And machine learning is the practice of trying to automate that away. Obviously, a great example of that is robotics. And actually, the one thing I have against Professor DeAngelis' talk is that it's so cool working with robots. Robots are so cool. Like in software, where the back-end engineers look at the front-end engineers and say, I wish I had some front-end that I could show off to people because people would be amazed. Because all we've got is just that curl that we can do. And it's taken months to write that code. And all we do is just do a curl. And we're like, yay! And everyone's like, well, it's just a curl. And then the front-end guys have got, look at all these visuals and it's the same. I do data science. I don't do robotics. I wish I did robotics because it's so much cooler. And then we've got another really good example. I'm not sure how many of you are cucumber growers here in Berlin, but if you were, what you could do is you could write an algorithm that would classify big, medium, small cucumbers and whether they were straight or bent. So another really esoteric implementation of machine learning there, but it just goes to show the diversity of industries that these type of techniques are being applied to. So hopefully that makes a little bit of sense. Analytics in the business side of things comes from the idea of trying to convert data into actions, actionable insights. So companies at their heart are information processors. The companies that can absorb, parse, understand, and act upon that information are going to be at an inherent advantage compared to their competitors. And this is what analytics does. It attempts to take that data and provide simple, actionable insights for people to act upon. One of the best examples of analytics is Google Analytics, because so many people are familiar with it. This is very focused towards web-based businesses, but there are equivalents for many other sectors, manufacturing and offline type businesses like that. Now, big data. This takes the crown. Well, this is the second crown. On the top is AI, and I get really annoyed at the word AI. I also get annoyed at the word big data for very similar reasons. I need to look up who actually coined the term, but the term big data just means lots of data. That's it. It's not really a thing. It's just an adjective to describe how much data you have. Lots of it. And it doesn't even make English. It doesn't even make sense. Big data. I don't know. There's a big amount of audience here today. It doesn't even make sense in English. But it has become a genuine discipline in its own right, because handling and scaling to handle lots of data is actually a really hard problem. But to be honest, I think of it as more of a computer science type problem. And it's probably something that many of you do on a day-to-day basis. But it has formed a part of data science because of the vast amount of data that's now required to do some of these advanced applications. And you can see a couple of projects on there. And there are also presentations in their own right on these technologies. So yeah, big data, very simple, lots of data. And we get to another hype term, but actually this is one of the ones that does genuinely have a lot of promise. So deep learning, I like to think of deep learning as one of the first widely used general purpose learning frameworks. And I say that because all the way back in 1950 when Alan Turing started talking about these types of things, he was always talking about them in terms of a generic computing framework. This is the first hints of that coming true. Its base unit is a neuron, and it comes from the idea of our brains again. And at its heart, it's actually just a simple linear function. So if you go back to your school and you do the y equals mx plus c, that is all a neuron is in a neural network. Okay, it's not too complicated. A few technicalities of nonlinearity of blah, 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 blah. But the idea is that when you stack many of these neurons in very, very complex patterns, they're then able to mimic and simulate and predict very, very, very complex processes. And that's what allows them to work on this high-dimensional, uber-complex data. And that's actually a big problem as well. Because if we go back to Professor DeAngelis' talk again at the start, he was always talking about feedback and how everybody's problems always solved by feedback. Unfortunately, this is so complex. This has interconnections and feedbacks between hundreds, thousands, tens of thousands of neurons, and these become highly, highly unstable because you can't control all of them with, in such a minute way. So when we work with deep learning, what you'll see is a lot of the blow-ups that you saw on the graphs that he talked about. So a lot of the work over the last 20 or 30 years has actually been trying to find ways that can control that. And now we do finally have that. And that goes on in a process called training. We take these highly complex models and we train them, we basically force them, we kick them into working. And the problem with that is that it's great during the training process, but then when we release it into the wild, it then doesn't have any feedback anymore. We're asking it to do things on new data. There is no feedback inherent in that design. And that's what happens when things go wrong. So I keep talking about one of my best examples is Tay.ai, and it was this Twitter bot that Microsoft created in 2014. And it was a great example because a lot of really smart guys produced a Twitter bot that was great at answering questions in a human-like way. It would definitely pass the Turing test. The problem is that they kept some feedback in there. They tried to learn from the new tweets it received after it had been trained. Okay? But the problem they didn't realize that the world was full of sadistic engineers like you. And instead of it being a fantastic product, people tried to break it. So they sent it all sorts of crazy tweets, really horrific tweets and texts, and finally this bot started repeating things back that were definitely not nice. And because of that, after only 24 hours, it was shut down. And actually, they deleted everything. You know, the Microsoft police just brought a brush and just moved everything away. You know, they still own the domain, but the page is gone. There's no mention of it at all. And it's a shame because it was a really good. It was a great piece of work. It just went wrong. Okay. And data mining, I like to talk a little bit about data mining as well because it is still really, really important. And data mining is 20, 30 years old. It's the process of trying to collect and parse and understand the data, to try and infer what the process is underneath that data. And you know, it's still really important today. Because we've got all this data, but we still have to understand the underlying processes. We can't just apply these black boxes and expect everything to work as well as we'd like. So how is this related to AI? Well, I think what I'd like you to try and realize is that all of the advanced products that you see today, you know, the drones that you see, you know, they are very sophisticated and they're very impressive, but they'd come back, I mean, that's even more fundamental than data science. I'd say that's almost just electronics, you know, it's just control theory. And it's very advanced control theory, but it is just that. All of what Google has just become very, very good at the big data problem, handling huge amounts of data and reducing that into a readable format. And you can generally take most products and split them down in this way. You know, there's no magic involved. It's all, well, to be honest, the majority of it is just hard work and engineering, more than, you know, magic. But there is some relation to AI, because if we try and think about what we do in a day-to-day life. I should have changed this graph a little bit. I think it's a bit too complicated. What I'm trying to suggest is that our human model, our psyche, we do things that are sort of future-oriented. We do things that are rooted in the now, in this moment, and we also do things that are related to the past as well. And these map very well to the various machine learning disciplines. So we've got prediction and classification there. They're very future-oriented tasks. We're trying to do something, predict something in the future, possibly. And then we've got observations, and the various techniques around the observations, the things like the data mining and feature engineering and stuff. That's all rooted in the now. And then we've got stuff in the past. You know, if you go to a library and look at its catalogue, it's been catalogued, it's been taxonomized. And people have spent an entire lifetime just cataloguing certain things. So it's definitely an important part of our psyche. And there's a map and a range of machine learning tools and techniques that we can perform to do the same things. So if we excel at all of those things, then maybe we can say that we're starting to replicate the functions of a human. To demonstrate some of these ideas and some of these faculties, again, I'm going to go back to my kids. And a bit more recently, when my daughter is about 3.5 now, I've been trying to teach her how to catch a ball. Because as it turns out, it's really hard. You don't think of it as being really difficult, but it is. And when she started, all I did was just set the task of just throwing something in the air and catching it. And the first thing that she did was this. She just stood there. That was my wallet. Don't steal that. You know, she got the throwing bit okay, but she had absolutely no idea how to catch it. It's something that she had to learn. And you know, the first thing that she needs to do is firstly just observe. This is an observational task. We need to look at the ball. So I tried to teach her to look at the ball, but she was concentrating so hard on what I was trying to teach her, she did this. I got her to physically move away from me so she wouldn't look at me. But instead, she did this. She sort of looked, she was sneaky and just went like that instead. So she actually started to try and mimic me, you know? She saw that I was doing this, so she tried to do this, but she was still concentrating so hard on what she was doing. So, you know, but there's a number of different tasks involved. The first one is she's got to classify that it's a ball, right? The best example I've got of this is, you know, when you're chopping something on the work surface and you drop the knife off the work surface. You do this little dance to try and escape the falling knife. It's like a 21st century Western, you know, shooting dance. And that is a classification in an instinctive manner. Because if I was to drop some food, I would actually try and catch that with my foot. You know, I wouldn't jump out of the way. But I'm from Yorkshire, I'm quite tight, you know, we've got to save everything. And this is an instinctive thing that we do. It's something that we've learned over many, many, many years, and she hasn't learned how to do that yet. And the second is observation. She needs to observe the trajectory of that ball in flight. She needs to estimate the velocity and the gradient and the position of her body. And that's all really hard to do as well. Interesting for American baseball players, they have learned to watch the pitcher as he's throwing the ball, because the ball flies so fast, they don't have time to react to the ball in flight. They're using features, they're using dimensions that they've figured out over their careers of watching how the pitcher throws the ball. So it's quite interesting when you get an unconventional pitcher, you know, one that's throwing it from the floor or up high, or has got a very strange throwing action, that they really struggle. And that's purely because they haven't had enough practice or experience to learn the features of those types of pitches. And then finally, she needs to make a prediction. And this is the exam question that we all probably got on our exam for maths or physics. And actually, it's still a hard question to solve because there's lots of variables in there. We've got some velocity. We've got to calculate the differential of that velocity. We've got to take into effect the gravity and things like that. Yet somehow, with lots and lots of practice, we are just able to automatically do that. So it's actually no surprise that it is actually quite hard to catch a ball. And it will take my daughter years of practice. And that's kind of a lesson for everything. It's a lesson for machine learning, because what that tells us really is that we need lots and lots of data. We need lots and lots of examples to be able to train our models to do the things we want them to do. If you're learning a new subject, you need to take time to practice and practice and practice. And then eventually, you will get better. Okay, so now let's show you some examples. I'm going to show you a couple more robotics examples again because they're so cool.
Shaky reside in a large PDP-10 computer and occupy over 300,000 36-bit words of
Apologies,
storage.
I'm on the wrong screen.
Shaky communicates with a computer
This is Shaky
over
the
a radio
robot.
link.
This is about 1960, 1965. Engineers
We
still
use
look
a
the same today,
teletype
look,
to
too
give
much hair on the head.
instructions to the computer programs that control Shaky.
And he's using a teletype printer. If you've never
Shaky
seen one before,
reports
that's what
back
it looked
to us
like. That's what
using
you'd
the
code
teletype
the instructions on.
and the cathode ray tube display.
Very advanced monitor there.
Another intermediate level action pushes
And
the
this is
named
talking
object,
about
box 1 in
the,
this
you know,
example,
Shaky was
to a
important because we didn't
location
tell it exactly
specified
what
by
to
a pair of
do. We didn't tell
coordinates.
it to go left or go right. We just tell it to go to a specific place. It would
A
figure
feature
out
of the
by
intermediate level
itself
actions
how
is their
to get
ability
there.
to recover from unforeseen accidents.
And I like this. We're just going to watch this little bit
Our
because
gremlin, Charlie, symbolizes an agent of change unknown to Shaky.
I love the video
Tell
editing
him
there.
that the box has slipped off the push
Fantastic
bar,
cutting and
but his cat
pasting
whiskers
there.
tell him where the box is.
Okay, so that was about 1966 to 72. That was the state of the art, and it was pretty impressive. In about 2016, this is from Boston Dynamics, and again, this is just watch this little bit. I'll stop talking for a second. That's what drunk robots look like. And I like this example because it actually demonstrates anthropomorphism and anthropomorphizing with inanimate objects. Remember, that is a robot, okay? But as we're watching this is what's going through my head. I don't like you. Stop that. That's really mean. Just let him do his job. He's got a job. Just let him do it. Don't. Oh, you absolute. You know, and it goes to show how we can actually feel for these inanimate objects. So I find this fascinating. And we'll just play one more example of the man being mean. Oh, what an idiot! Don't like that guy. But you know, as a little dig to Professor Andreas as well. Oh, you can't see that. Robots are so 1970. You know, nobody's interested in robots anymore. Let's move on to the more advanced stuff. And I've got an example here that is working with a newish data set called the Stanford Question Answering data set. And this is really cool because it's a data set that's used to tackle a specific type of problem with text. And the problem is, given some free-form text, can you answer free-form questions? And that's really tough. It's a really tough problem to solve. So let's just have a look at, I don't know, a couple steam engine. And we'll have a look at the examples here. So the text comes in as like this short excerpt from something like an encyclopedia or Wikipedia or something like that. And then we are given some ground truth answers. So these are the true answers that the algorithm is supposed to predict. For the question, along with geothermal and nuclear, what is a notable non-combustion heat source? And you know, solar, super. And there's a couple of different potential right answers here. And I've got one of the implementations of one of the most recent solutions to this. And I don't know, if we just pick one of the pre-written paragraphs, then you can see that it's answering those free-form questions pretty well. And generally, if you go through all of these questions, you'll find that it gets the right answer. But the really cool thing is that if you just ignore this, was it? I said generally right, okay? I didn't say completely right. Dearie me. Bunch of smart asses in the audience today. Okay, so don't ask me how, but I've just got the full text of Hitchhiker's Guide to the Galaxy here. And I'm going to ask it a free-form question. First, I'm going to ask a question which I know it gets the right answer for. How big is a dog? Who typed that into my search history? How old Arthur Dent? Oops, and submit. And after a couple of seconds or so, we should hopefully get an answer. And there you go. And I believe that's correct. Some more of the more nerdy in the audience might be able to correct me. But this is a really interesting answer, assuming it is correct, because it's actually, you know, this isn't even a number. This is a word that is pulled out of the text. And I believe actually that in Hitchhiker's Guide to the Galaxy, there's actually not that many numbers at all. Most of the numbers are all written as words. So this was able to interpret my question asking for a number, even though no numbers exist in the text. So this is a really interesting result. Let's ask something. Let's ask something a bit more difficult. And I think that this kind of gets the wrong answer. It gets a bit confused. Yeah. So what planet is Zaphod from? Galaxy. I don't know. That's probably part of a longer text, but it's got a bit long. But we're all here to do one thing and one thing only. Let's see what it gets. I promise you, I have not programmed that. That is purely the algorithm choosing for itself what life is all about. And either it's already mastered satire, I'm not sure. I hope that it has. Either that or it's already becoming evil, and we should stop it right now. Okay. And I think we're about out of time, so I'll just finish up. Is that right? Yeah. Okay. So, you know, what is the meaning of life? The meaning of artificial life. If we take Turing's view, machines are already acting like humans. So we could ask a human, what is the meaning of life? It's the same question. And I'm an engineer, and no way am I going to try and ask those sort of questions. So I'd just like to end. If you're interested in data science, I've started a new website and business, trainingdatascience.com. It gives away some free training in data science and also helps people learn online what data science is. So with that, thank you very much. Thank you.
I have a couple of questions here, and I know we
Excellent.
are over time, or soon will be at least.
Okay, I'll be quick.
So I'll pick just one of them. Are you looking forward to use quantum computing in conjunction with data science?
I don't know. To be honest, I don't even know where that's going to go. I mean, first, there's lots of practical issues with quantum computing, and when they become mainstream, they're just going to, blow open the whole idea of being able to compute these complex processes, and they will then become possible. So I honestly can't even envisage what is going to happen once we have the ability to predict random processes. I don't know. I mean, ultimately, if you could predict the position of every atom in the universe, you are predicting the future. And if quantum computing can even achieve some, level of that, if they can then work on some physical level, then the world's the oyster. Yeah, I have no idea.
Thank you. For the rest of the questions, please feel free to come and ask them in person here.
Thank you very much.
And I can see Michael, yours already here. Welcome, Michael. Looking forward to your talk in 20 minutes. And just one final note, the example with the cucumber classification that you showed, this is actually one of the topics for the last talks today. So, see you around.
Yay.